Hello again. Today we're going to be looking at some tricky problems that involve the definition of the derivative. These are problems that you aren't just simply using your shortcut derivative rules, but you need to use the definition of the derivative and some tricky algebraic manipulation to solve. Okay, so here's one. We're trying to, f of x is a differentiable function. So what does differentiable function mean? A differentiable function is a function whose derivative exists, okay? If they say that, like, f of x is differentiable at x equals 2, then all they're saying is the derivative exists at x equals 2. If they say it's a differentiable function, it means the derivative exists everywhere for all real numbers, okay? So, assuming f of x is a differentiable function, evaluate the limit as x approaches 4 of x squared f of x minus 16 times f of 4 over x minus 4. So this should look a little bit familiar. It looks sort of like the definition of the derivative at x equals 4, which I'm going to write right here so we can remember what it is. So the derivative at x equals 4 is a limit as x approaches 4 of f of x minus f of 4 over x minus 4. Now there is a second way to write the derivative at 4 involving a limit as h approaches 0, but that's not what this looks like. It looks closer to this, so obviously we're going to take advantage of this. Okay, so some things I notice is that the bottom's the same, but the top has this extra x squared in front of the f of x and a 16 in front of the f of 4. Okay, so here's what we need to do to simplify this. Okay, here's my thinking. Since I have an x squared in front of this f of x, in this formula, if I multiplied by x squared times this, I would want to multiply by x squared times this as well, and then maybe I could just factor the x squared out somehow, okay? So what I want to see is x squared f of x minus x squared f of 4. So I'm going to introduce a minus x squared f of 4. Now, I can't just do that for free, so I'm also going to add x squared times f of 4. That way, this equation is the same as the original. Okay, and then the whole point of that is then I can split this up into two fractions, like that. Okay. Now, as I said at the start, I can factor out the x squared out of this, which is going to leave me the derivative pattern. Meanwhile, over here, I can factor an f of 4 out of both terms on the top there. So I can write that as f of 4 times x squared minus 16 over x minus 4. And notice when we're doing a limit of something plus something, I broke it up into two separate limits, which is a limit law. And then limit of something times something, you just do limit of the first times limit of the second. Well, the limit of the first, that's a polynomial, so you just plug in 4 and you get 16. So that's going to go to 16. This is the definition of the derivative at 4, which we know exists because it's a differentiable function, and therefore this limit must exist. Okay, and then over here, f of 4, I don't know what it is, but it's a constant. So constants can be factored out of the limit. So the f of 4 just pops right out. And then times the limit of this. Now, if you try to plug in 4, you get 0 over 0, which is indeterminate, so we need to simplify. At the top, we can factor in x minus 4 times x plus 4. Then we see we can cancel off the x minus 4s off the top and bottom, just leaving x plus 4. Now we have a polynomial, so we can simply plug in 4 and we get 8. So that's going to become an 8. So the final answer is 16 times the derivative of f of 4 plus 8 times f of 4. Okay, so a little bit of a tricky problem. Let's do one more. It's going to be a little bit similar, but it's going to be different. Once again, we're going to assume that we have a differentiable function. And this time, let's do a limit as x approaches 9. And let's make the top f of x minus f of 9 over square root of x minus 3. Okay. Once again, this looks sort of like the definition of the derivative at 9. So let's write that down. The derivative of f at 9 would be the limit as x approaches 9 of f of x minus f of 9 over x minus 9. This time, instead of the top being different, it's the bottom that's different. So makes it a little bit different. So we sort of need to manipulate this so that the bottom is going to become x minus 9. And me, whenever I see square roots, and I know I have to do some sort of simplification, my mind immediately jumps to using the conjugate. So it turns out that that is exactly what we want to do. So I'm going to take this equation and multiply the top and bottom by the conjugate, so square root of x plus 3. Multiply that on the top, and multiply by that on the bottom. Okay, don't bother to actually multiply the top out, it would be a mess. But the conjugate is designed that when you multiply it by the original equation, it simplifies nicely. First would be square root of x times square root of x, which is just x. Inner and outer cancel. And last is minus 3 times plus 3, which is minus 9. So the bottom becomes x minus 9, which is exactly what we want. Okay, so the bottom becomes x minus 9. And then I see that this part right there is the derivative pattern. So this is going to become the derivative of f at 9. And then we still have to do the limit as x approaches 9 of the rest of it, square root of x plus 3. And we can simply plug in, giving us 3 plus 3, which is 6. So we get 6 times the derivative of f at 9. Okay, one more problem, also related to the definition of the derivative. Let's say that someone comes up to you and they said, I've got a new way to write the derivative. Let me show you, okay? And they say that they're going to define the derivative of f at x to be the limit as h approaches 0 of f of x plus h minus f of x minus h all over 2h. Now, I'm saying this is equal, but that's his claim. Maybe I shouldn't put equal. Maybe let's just leave this off, and we're going to evaluate it and see if this really is an alternate way to define the derivative. Okay? So, once again, let's write down what the derivative really should look like when you're using a limit as h approaches 0. It should be the limit as h approaches 0 of f of x plus h minus f of x all over h. That's the pattern for the derivative at x. Okay? So then let's try to manipulate this. Okay, I've got f of x plus h, but I'm missing the minus f of x. So just like the first problem, let's add that back in. So I'm subtracting f of x, so to balance that, I'm going to also add f of x. Okay, then I can break that apart into 2 separate fractions. I'm also going to factor out the 2 out of the denominator. which gives me this, okay? This is exactly the pattern for the derivative. So this is half of the derivative of f of x plus. Now look at this one right here. As h approaches 0, but instead of like f of x plus h minus f of x, it's f of x minus h, okay? To prove that this is an alternate way to define the derivative, let me show you using a change of variable. What if we were to let a new variable y be equal to negative h? As h approaches 0, well, y's negative h would still approach 0. One time we're still going to go to 0, so I can just change the limit as approaches 0. Okay, that's going to be f of x. Oh, y looks like a variable. Let's use the letter a instead of y. So negative h, the limit becomes limit as a approaches 0. This negative h is going to become a plus a, so x plus a, and h would equal negative 1 times a. We can multiply by negative 1 on the top and bottom of this fraction, which would give us, that would become positive, that would become negative, and the bottom would become positive. And then this looks exactly like the derivative, just we're using the letter a instead of the letter h. So still going to be the derivative of f of x. Therefore, this is a half of the derivative of f of x. So my friend says that proves that this is an alternate way to define the derivative. However, there's one mistake that's made here that makes this not an alternate way to define the derivative, okay? And that is one little step we did way early on, adding and subtracting f of x, okay? What if the point at a particular value of x didn't exist? Then we're adding and subtracting something that doesn't exist, and you can't do that. You can only add and subtract a constant, a number. Okay, see, in the original equation, there is no f of x. So if at a particular point x, the function doesn't exist, this limit still could exist. So okay, this does equal the derivative at x, assuming the function exists at x. So if the function exists at x, this is an alternate way to define the derivative at x. But if your function doesn't exist at x, then this gives you a value where the actual derivative equation wouldn't, because this would be undefined, but this, no part of it is undefined. Let me just show you graphically real quick what I mean by this. See, what our derivative is doing, the actual derivative equation, is at some value of x. You know, we have an f of x, and then we pick an h to the right of it. So this is f of x plus h, sorry, not just h, f of x plus h. And then this is the slope of the secant line, and then as h approaches 0, the 2 points get closer and closer together, and it becomes the slope of the tangent line. That's how it's supposed to work. Now let's take this equation. Oh, and notice, if this point didn't exist, then we couldn't do a slope of a secant line because f of x would be undefined there. But this problem, the way that it tackles it, is it picks 2 points, one to the right, one to the left, and it calculates slopes repeatedly, ignoring checking to see if that point even exists. So that's why this is not an alternate definition of the derivative. I've seen it come up in some homework problems from UT before, and if they do claim it is an alternate way to define the derivative, they need to be explicit that this is only true if you know that the point f of x exists, then the derivative, this is the derivative of f of x. Okay, that's going to be it for this video. I think in the next video, we'll go on and look at some more derivative rules, expanding it until eventually we get all of the different types of functions and eventually chain rule and applications Anyway, I hope to see you in the next video. Have a good day.